All right, example 2. And this is what you have to do when you have repeated linear factors. Now, when they're repeated, that shortcut, the finger method, doesn't work quite as well. So we'll have to do it the old way. So here's the question. So I'm going to start factoring it. Take out an x squared and get left with an x minus 2. Okay, you see the x squared. That's what's going to mess up the finger method. So we have 5x squared minus 3x plus 2 over x squared x minus 2. Here's the deal with this. You could have a fraction that has a denominator of x. You could also have another one that has a denominator of x squared. And you could have a third one that has a denominator of x minus 2. So, multiplying through by the common denominator. And I actually could use the finger method on the c. Let's just go off to the side and do that. The c, x can't be 2. So if I cover up the x minus 2 on the left side and stick 2 in, I get 2 squared is 4 times 5 is 20. 20 minus 6 is 14. 14 plus 2 is 16 on top. And then 2 squared is 4. C is 4. And I could use it for the x squared, but I won't. I'll leave that one alone. So multiplying through by the common denominator. On the left side, you just get the numerator. On the right side, you're going to get 1x canceling, so you get this. Now you get x squared canceling, so you get this. And here you get the x minus 2 canceling, so you get cx squared. So I have ax squared minus 2ax plus bx minus 2b plus cx squared. So my x squares are there, which means, and I'm going to take a little shortcut here to save some paper, 5 must equal a plus c. Then I'm going to go to the next one, the x's, the negative 3, the negative 2a, and the b. Those are all my x's, so that says that negative 3 must equal negative 2a plus b. And then finally, constants says that 2 equals negative 2b. Okay, so that's nice. B is negative 1. So if b is negative 1, I could go right here and say negative 3 equals negative 2a minus 1. So negative 2 is negative 2a. So a is 1. And then if I went back and stuck the 1 into the top equation, I will get that c is 4, just like I did with the finger method. 5 equals 1 plus c, so c must be 4. So this question wanted us to evaluate the integral of this. So we're supposed to be integrating this whole nonsense. So my complex fractions turn into a was 1 over x, my complex fractions, my partial fractions, minus 1 over x squared plus 4 over x minus 2. And I'm supposed to be integrating this, so I'm going to put an integral in front of each one. So this one's nice. It's the natural log of the absolute value of x. This one, however, is x to the negative 2 dx. So you raise the power and you flip it in front. And then the last one, now the only thing you got to be careful of when you're doing these natural log integrals, you've got to check. You've got to make sure that the du is just dx. Because if it's not, if there were like a 2x minus 3 there, or 3x minus 2 there, you'd have to stick a 3 in and a 1/3 out, because you wouldn't have your derivative of the inside. So just be careful of that. And so now combining stuff, I end up with a 1 over x, that middle term, and then the two natural logs can go together. The absolute value of x has to stay with bars, but the second one doesn't need the bars because it's actually being raised to the fourth power plus a constant. The next thing we're doing is called irreducible quadratic factors. And the problem with this is you get something that doesn't factor out all the way, and so you get left with a mess. You get left with pieces that don't factor. And so when that happens, you have to break them down differently. For example, when we had something like x minus some number, let's just call it a, then we just put a capital A over it. But if we get something like ax squared plus bx plus c that doesn't factor, it's a squared term, so the one on top has to be a linear term. It has to be 1 degree lower. This is supposed to be bx, not exponent. Okay, the bottom is a quadratic. It's got an exponent of 2, which means the factor on top of it would be a factor of 1. So you have to have an ax plus b. So another example would be is if I have ax cubed plus bx squared plus cx plus d, the degree on that is 3, which means my thing up top would have to start with a square and then have an x and then have a constant. So it's always 1 degree lower. So it makes for a mess. Example 3 wants us to set up the partial fractions, give the appropriate form, not necessarily actually finish the problem. So part A says we have x squared plus 1 over x to the fourth minus 4x cubed minus 32x squared. Okay, so if I factor that, the bottom, I can take an x squared out of it, and I'm left with x squared minus 4x minus 32. Combinations for 32 that add to negative 4. That one actually factors. That would be x minus 8x plus 4. So x is the repeated factor, so I've got to take care of that. So this would break into a partial decomposition of an a over the x, and we did one just like this a minute ago, a b over maybe an x squared, a c over x minus 8, and a d over x plus 4. So that one factors down, so it's not irreducible. But part B does have an irreducible one. It says 10 over x minus 2 squared, x squared plus 2x plus 2. Now you can try all day long, but x squared plus 2x plus 2 is not going to reduce. So our x minus 2 is to the power of 2, so I have to consider that maybe there's just 1. Oh, and then maybe there are 2. And then this last thing that doesn't factor, since it's an x squared, I have to have an x up here, so cx plus d would be its breakdown. And now we're going to do one that you actually have to integrate, but not this one. And it's not going to fit on this page, so I will start it on the next page.